Okay, welcome to part 2 of our SAT math series. This one's called Advanced Math. It gets away from the linear equations and things that we did in part 1. And we get into some polynomials with exponents that are greater than 1. Okay, we'll also talk about radical expressions, rational expressions, quadratics, and solving systems based on these things. Okay, this portion of the test makes up 16 out of the 58 math questions. So again, it's a pretty good chunk of it. So here we go. Alright, the first thing we have to get comfortable with is our exponent rules. Okay, so exponent rules, algebraic expressions with exponents, we can always simplify them using these rules. Okay, so this first one here says x to the power of m times x to the power of n. When we're multiplying two exponents of the same base, we can then go ahead and add their exponents together. Okay, so an example, if we had 2 to the power of 2 times 2 to the power of 3, okay, to simplify that, because our base is the same, we can rewrite that base and then just add the two exponents together. So this would give us 2 to the power of 5. Okay? So that's a real quick explanation. So the next one here, okay, when we're dividing exponents of the same base, instead of adding like we did when we multiplied, now we'll just subtract those two exponents. So for instance, if we had now 2 to the power of 5, we're divided by 2 to the power of 2. Okay, again, our base is the same, we can rewrite it, and we would just be 5 minus 2. 2 to the power of 3. Okay, so these will help us simplify our equations and let us work with simpler numbers to deal with. Okay, so here is an exponent, okay, that's raised to another exponent. Okay, so now when they're the same, we will now multiply those exponents together. So again, if we had 2 to the power of, say, 4, okay, if we were like this, okay, we could go ahead and multiply those two together. So 4 times 3, it would give us 2 to the power of 12. Okay, so if I were to rewrite that one actually, okay, 2 to the power of 4 raised to 3. If I were to write this out the long way, it would be 2 to the 4 times, sorry, that's a multiplication, times 2 to the 4 times 2 to the 4. Okay, and now this would be 2, 4, plus 4, plus 4, which would still be 2 to the 12. Okay, so real quickly, those are exponent rules, and we will have to use those on this section of the test. Okay, so some more rules we need to be familiar with. Okay, negative exponents. When we have a fraction, okay, with an exponent on the bottom, so say it was 3 to the power of 2, okay, that is the same thing as saying 3 to the negative 2. Okay, and vice versa. If I had 2 to the negative 3, okay, I could go ahead and rewrite that as 1 over 2 to the positive 3. Okay. Okay, an exponent of 0, this is a special case where it doesn't matter what our base is. So in this case, it doesn't matter what x would be, that would still be equal to 1. So 1,000 raised to the 0 is 1. Okay, anything raised to the 0 would be 1. Okay, and then here we get into fractional exponents, which are just roots. Okay, so I could read this as the nth root of x. Okay, so if we had, say, okay, so that we would read this as the cubed root okay, or the third root of x squared. Okay, and we could rewrite this as a fractional exponent as x squared divided by 3. So x raised to the power of 2 over 3. Okay, and then again, those will help us simplify. Okay, so here's an equation. So this equation here, sorry, okay, this equation here, okay, the first thing we notice is that we're dealing with exponents, okay, and whenever we're dealing with them, what we want to do is try and make them the same base. Okay, so that 8 to the x on top, okay, we can rewrite the 8 to the x on top. I know that 8 equals 2 times 2 times 2, which equals 2 to the power of 3. Okay, so I can rewrite the one on top as 2 to the power of 3 raised to the x over 2 to the y. Okay, so when I do that, I want to use my exponent rules. Okay, I have up here I have a base raised to another exponent. Okay, so I'm going to go ahead and multiply those two together. So when I do that, I rewrite my base. I have 2 now times x, so 2 to the 3x. Okay, and I still have 2 to the y on the bottom. Okay, so my bases are the same. My bases are 2. Okay, and I'm dividing them out. So what I want to do is rewrite my base. 3x minus y. Okay, so now I'm just going to do some substitution. Okay, I know that 3x minus y equals 12. So I know that 2, and from that 3x minus y equals 12, I know that that's the case here. Okay, so this can simplify to 2 to the power of 12. Okay, so for my next question here, okay, I want to use those same rules. Okay, and again, I can combine them in any way I want, just like the first example there. Okay, I had to combine a couple of them. Okay, but ultimately it helped me simplify that equation into a number that I can handle. It's 2 to the power of 12. Okay, so here, this next one, first, I notice my a's are the same, so I can go ahead and combine those exponents. Okay, when I do that, I get a 2x plus 3, and I know that equals a to the power of 15. Okay, so here, what I want to do is I want to now compare these together. Okay, my a's are the same, so now I can just look at the exponents. Okay, doing that, okay, I know that 2x plus 3 has to equal 15. Okay, when I get to here, now I'll just solve this algebraically. So I'll subtract 3 from here. From both sides, I end up with 2x equals 12. Okay, which is just x equals 6. Okay, and I'll do the same thing for the b's here. So if I were to rewrite this, okay, this is b to the y divided by 3. Okay, and that equals b to the 5. Okay, so just like I did with the a's over here, I'll now compare the exponents together. So I know that y over 3 equals 5. I'm going to multiply this by 3, and I'll multiply this by 3. And I just end up with y equals 15. Okay, so now I have values for x and y. And now I'll go ahead and plug into y minus x. So 15 minus 6 just equals 9. So my answer here is 9. Okay. So we'll move on to polynomials. Okay, polynomials are algebraic expressions that consist of any number of terms. Okay, so a polynomial, I could have 8 different terms, I could have 6 different terms, doesn't matter. Okay, in this case, here's a term, here's a term, and here's a term. Okay, so when I say 6 or 8 terms, it's just a different variable with a different exponent. Okay, so in this example here, the coefficient of x squared is -3. Okay, so the coefficients are just the leading number in that term. Okay, so the coefficient of x squared is -3. The coefficient of x is 2. And then we have the 1, which is a constant value, which means it doesn't change. It doesn't have a variable attached to it. Okay, so when we're adding and subtracting polynomials, we collect like terms. And when we're multiplying polynomials, we distribute. Okay, so we'll get into some of those examples. Okay, so for this example here, I have 2 polynomials. Okay, here's one, here's another one. Okay, and they're separated by a subtraction sign in the middle. Okay, so what I want to do to these is collect the like terms. Okay, so what I'll do is I'll color code the like terms. It's a good idea for you to circle like terms, maybe square another one, underline another one, just so that you have a visual representation of which ones are the same. Okay, so for here, I have an x squared y. I have an x squared y here. Okay, I have a y squared, I have a y squared. And finally, I have an xy squared and an xy squared. Okay, so I'm going to collect these together. Okay, very important, okay, that you distribute in this negative sign. Okay, if it was a positive 2 here, you would distribute that positive 2 into the second polynomial. Okay, so first one I have xy squared, okay, minus a negative xy squared, so that becomes a positive x squared y. Okay, the orange ones I have negative 3y squared minus negative 3y squared, so again positive 3y squared. And then I have 5xy squared minus a positive 3xy squared. So that becomes minus 3xy squared. Okay, and now I will just add together their coefficients. So here I have 2 x squared y's. Okay, my orange ones I have a negative 3 and a positive 3, so they cancel. And then here I have positive 5 minus 3, so I'm left with 2 xy squared. So C is my correct answer. Okay, so the second one here, okay, I'm multiplying 2 polynomials together. Okay, the question says, in the equation above, b is a constant. If the equation is true for all values of x, what is the value of b? Okay, so my first step is I want to distribute in and multiply these 2 polynomials together. So when I do that, okay, first I want to distribute the x squared into x plus 3, and then I'll distribute the bx, and then I'll distribute the negative 2. Okay, so when I distribute in the x squared, I have x squared times x, so x cubed, and then x squared times 3, which is positive 3x squared. Okay, so now I move to the next term. So I have bx times x, which is positive bx squared, plus 3bx, and then I have negative 2 times x, which is just negative 2x, and negative 2 times 3, which is negative 6. Okay, so now again, to simplify this, I will just collect all my like terms. So x cubed is by itself. Okay, then I have 2x squareds. So what I'll do is combine their coefficients. Okay, so I have 3 here plus b here. I'll combine those together. For my x's, I'll combine their coefficients. So I have 3b minus 2 times x, and then I'm left with just minus 6 at the end. Okay, so looking at this, my x cubed here is the same as my x cubed here. My negative 6 here is the same as my negative 6 here. So the only coefficients I now have to worry about are the ones that have a b in them. So the coefficient of x squared. Okay, so what I'll do now is I'll compare this 3 plus b to the coefficient of x squared up here. So I have 3 plus b equals 6. I can go ahead and simplify that, just solve for b. I'm left with b equals 3. Okay, if I do the same for the coefficient of x, I have 3b minus 2 equals 7. And again, solving for b, I'm left with b equals 3. Okay, so b is 3 for both of them, so my answer would be b. Okay, so that's the basics of polynomials, collecting like terms and distributing. Okay, so moving to rational expressions. So a rational expression, all it is when there's a polynomial on the top, or the numerator, and a polynomial on the bottom, which is the denominator. Okay, so again, I will have to either add and subtract rational expressions, or multiply them together, or divide them. Okay, so the first thing we'll talk about is adding and subtracting. Okay, so because rational expressions are two fractions, okay, anytime we're adding them together, we have to make sure that their bottoms are the same, so a common denominator. Okay, so for this example here, I have 3x plus 9 on the top, okay, x minus 3 on the bottom, and then I'm adding x plus 2 over x plus 3. Okay, so again, to add them together, I need their bottoms to be the same. Okay, so the easiest way to do that is I will multiply this first equation here by the bottom of the other equation. Okay. And then I'll multiply the second equation by the bottom of this equation. Okay, this will ensure that when I combine them together, my denominators are the same. Okay, another thing to notice here is that 3x plus 9, okay, we can factor this out and make it a little bit simpler. Okay, both these terms I can pull a 3 out of. Okay, it'll just make it a lot easier to deal with at the end. Okay, so combining these two together, okay, and then still on top I have an x plus 2, x minus 3. Okay. And I know now that my common denominator is x minus 3, x plus 3. Okay, so now it becomes a matter of expanding and simplifying. Okay, so when I get to this step, now what I want to do is expand, okay, the top part of it, and I'll do that again by multiplying my polynomials together. Okay, so this x has to act on both of those, and the 3 has to act on both of these. Okay, if you're familiar with the term FOIL, that's what we'll be doing now. Okay, we will talk about FOIL a little bit later in this. Okay, but all we're going to do is just double distribution. Sorry. Okay, so I have an x times an x. I have a 3 times an x, so I have plus 3x. Then I have another 3x, and then 3 times 3, so plus 9. Okay, and I'll do the same thing for the second part right here. Okay, so I have x times x. Okay, x times negative 3, 2 times x, and then 2 times negative 3. Okay, and again, it's all over. When I simplify the bottom, I'll have x squared plus 3x minus 3x, and then negative 3 times positive 3, which is negative 9. Okay, so now I'll distribute in this 3 here. So I have 3x squared. Okay, I can combine these two together. And that'll give me 6x, and I'll multiply that by 3, so just to save some time, 18x plus 27. And then I'll just rewrite the second part here. Again, I'll combine these two together, just collecting like terms. Give me negative x minus 6. Again, that is all over the bottom here. So the bottom just simplifies to this. Okay, so I'll combine the like terms on top. I'm just left with 4x squared, okay, plus 17x plus 21. Okay, so when I get to here, there's really no other steps I can do to simplify this. Okay, so for this equation, I am done. Okay, so it feels like a lot of work. Okay, but as long as we're staying organized, keeping track of what we're doing, okay, it's all work that we are comfortable with. Okay, so this next equation. Okay, again, it looks fairly difficult, but all it's asking for is if t is a solution to the equation, what is the value of t? Okay, so all we want to do in this equation is just solve for t. Okay, so the first thing, there's a number of ways you can do this. Okay, but the first thing I will do is I will move all of these to the other side. Okay, so I'm just going to rewrite. I'll have a minus 2 over t plus 3, and I'll have a minus 1 over 4. Okay. So now what I want to do, okay, I have a bunch of fractions or rational expressions. Okay, so what I want to do is I need to find another common denominator. So again, the easiest way to do this is to take the first term, okay, and I'm going to end up multiplying it by the other two denominators. Okay, then I'll take the second term, okay, and I'll multiply it by the other two denominators, and then I'll take the third term and multiply it by these two denominators. Okay, so for the first part, okay, 3 over t plus 1, okay, and I'll multiply the top by t plus 3, and also by 4. Okay, what I do to the top, I do to the bottom, so t plus 3, and this is a 4. Okay, so now we'll worry about the second term. First I rewrite it. Okay, now I'm multiplying by t plus 1, and again 4. And I'll do the same with my third term, so minus 1 over 4. Okay, so I'm going to multiply t plus 1 and t plus 3 if I can fit it in. Okay, it's the same thing, t plus 1, t plus 3. Okay, so if we look at what we did, notice that now all the denominators here are the same. Okay, they're in a different order, but they have the same terms in there. Okay, so now what I'll do is I'll simplify the top part. Okay, so my first part, I have 12 t plus 3. And now I know that the bottoms are the same, so I can combine them all together. Times 4. Minus 8 is t plus 1. And then I just have minus t plus 1 over t plus 3. Or times t plus 3. And again, this all equals 0. Okay, so what happens now is, because I want to get t by itself, okay, I want to clear this fraction. So what's going to end up happening is, really, because I'm dividing by this denominator, to get rid of this denominator, I'm going to multiply it all, so both sides, and what happens is now I have 0 times this denominator, so really this is going away. Okay, so now I'm just left with the top part. Okay, so I have 12t plus 36 minus 8t minus 8. And when I FOIL out the green part, I have minus t squared plus t plus 3t Okay, so what I'm left with is a negative t. Okay, I have 12t minus 8t minus 4t. So I have no t's left. And then I have 36 minus 8 is 28 minus 3, which is positive 25, and this all equals 0. Okay, so if I solve for t, I have t squared equals 25. T equals plus or minus 5. Okay, but right here it's just looking for the value of t that's greater than 0, which is positive 5. So t equals positive 5. Okay, so again, feels like a lot of work. Okay, but as long as I'm remaining organized, okay, I just work through them one at a time, like I did with the different colors here, and then I collect my like terms at the end. Okay, so when I'm multiplying, dividing rationals, it actually ends up being a lot simpler than adding and subtracting them, because I don't have to worry about the denominators. I don't have to worry what the bottoms are. Okay, the best way of doing these, okay, is to factor the numerators and denominators as much as we can and see if we can eliminate common factors. Okay, the same thing for division. Division is actually the same as multiplication, except I'll just have to flip my rational expression over, and then I'll just end up multiplying it. Okay, so a couple of examples here. Okay, so this first one. Okay, what I want to do is first I'll worry about the tops. So really what I'm going to end up doing here is I'm going to multiply each factor over here by 5y to the 4. Okay, so if I do that, okay, I end up with 75 x squared y4, okay, plus 20 x y to the 7, okay, minus 15 y to the 5. Okay, so up here I'll just go through 4xy cubed times 5y to the 4. Okay, so just to show you where these came from, first I'll just multiply the coefficients together to give me 20. Okay, then there's no other x over here, so I still have just an x by itself. Okay, and then third, from my exponent rules, I can now multiply the y's together, so I end up with y to the 7, which is just 3 plus 4. Okay, so that's where this middle term is coming from. Okay, and I repeated that process for each of the values on top. Okay, so I'll repeat that same process for the bottom. Multiply my coefficients together, it's just 4. And now I'll multiply my x's together. Give me x to the 5. And I just still have just y to the 7. Okay, so now what I want to do is I want to simplify these exponents as much as I can. Okay, so I'll look at all the x squareds. Okay, and I actually don't have an x over here, so I can't do anything to this x to the 5 on the bottom. Okay, but if I look at the y's, I have a y to the 4, y to the 7, y to the 5. Okay, I want to take away the most y's that I can. Okay, in this case, so it's y to the 4. Okay, so if I take away a y to the 4 from each of these, Okay, I'm left with, I have no y's left here. Okay, I still have 3 here, and I still have 1 here. And on the bottom, I still have 3 here. Okay, so whenever it says simplify, I want to take out the most amount of a variable that I can. Okay, so if I can take a y4, y to the 4, out of each of those terms on the top and bottom, I'll go ahead and do that. Okay, and I couldn't take away any x's because my third term here did not have any x's to take away. Okay. So the next example, okay, again, I'm multiplying polynomials together. Okay, so the first thing I want to do to make my life a lot easier is to factor out everything I can. Okay, so I can't factor x plus 4 anymore. Okay, but I know that this x squared minus 1, okay, I can factor out into x plus 1 times x minus 1. Okay, we'll talk about that again a little bit later. But if you're familiar with quadratics and factoring and finding the zeros, okay, you know that x plus 1 times x minus 1 just equals x squared minus 1. Okay, again, my top over here, I can't do anything to it. Okay, and if I want to factor the bottom here, is there anything I can do to that one? Okay, there's nothing I can do to that one either. So I just have x squared minus 3x plus 4. I'll just rewrite it. Okay. But what that did for me, okay, is now notice that I have an x plus 1 on the top and an x plus 1 on the bottom. Okay, so common factor top and bottom, so I can just eliminate those. Okay, it's just reducing the amount of work that I have to do. Okay, so now I'll go ahead and solve. So now I have just x plus 4 on top. Okay, and I have x minus 1 times x squared minus 3x plus 4 on the bottom. Okay, so I'll go ahead and I'll simplify the bottom here. So still x plus 4. And I have x cubed. Again, I'm multiplying each of these terms by the x right now. Okay, so x cubed, negative 3x squared, and then 4x. Okay, now I'll go ahead and worry about the negative 1. Okay, so negative 1 times x squared is minus x squared, positive 3x minus 4. Okay, when I go ahead and collect these like terms, I'm just left with x cubed minus 4x squared plus 7x minus 4. Okay, and there is my final answer right here. Okay, I won't be able to factor anything else out to simplify that at all, so I'm just left with that. Okay, so moving on here, and now I have a division sign between two rational expressions. Okay, so first thing I want to do is rewrite, but now I'm just going to flip this second expression here, and I'm going to end up multiplying them. Okay, so once I flip them, now I will just follow the exact same multiplication rules. Okay, so the first thing again I want to do is factor out anything to see if I can eliminate. Okay, I can't factor anything out of an x squared or an x minus 5, so I'll rewrite those. Okay, x plus 2 can't change. Okay, but if I look at this second one here, the bottom here, I can take an x squared out of both of those. So if I take an x squared out, okay, I'm left with x plus 5. And now if we look, I can eliminate those two here. So again, by factoring things out, okay, hopefully I'll end up being able to eliminate, and it just reduces the amount of work I have to do. Okay, so now with what I'm left with is x plus 2 on top, and x minus 5, x plus 5 on the bottom. Okay, now, if this were to be a multiple choice question, okay, this right here may be one of the options. Okay? If it's not, it just means they went a step further and they expanded this out. So if I were to do that, I would have x plus 2 for x squared. Now I'll end up with a negative 5x and a positive 5x here. Minus 25. Okay, so my final answer would just be x plus 2, x squared minus 25. Okay? So your final answer may be like this, or it may end up looking like this. Okay, they just took it one step further. Okay, now, this next example looks like a lot of work. Okay, but really, what I want to do is the first thing I'm going to do is I'm going to just worry about the bottom here. Okay, so this is the addition of two rational expressions. Okay, so again I need to find a common denominator. Okay, so the first is I'll multiply it by the denominator of the other. Okay, and I know that I'm going to end up combining the bottoms to have a common denominator. Okay, so I'll go ahead and expand that out. I have an x plus 3 plus x plus 2. Okay, and my bottom will be x squared plus 3x plus 2x plus 6. So again, taking it one step further, 2x plus 5 over x squared plus 5x plus 6. Okay, which looks like A, right? But let's not forget that this was all 1 over all of that orange. Okay, so really this is the same as saying 1 divided by 2x plus 5 over x squared plus 5x plus 6. Okay. So knowing that, now it'll be 1 times I flip this fraction over. Okay, so again, whenever I'm dividing rational expressions, I want to flip and multiply. Okay, so that'll give me x squared plus 5x plus 6 over 2x plus 5. Okay, and 1 times anything is just anything. So my final answer here is B. Okay, so again, breaking it up into simpler problems. Okay, I just worry about this orange part to start with. Okay, and then I take care of the other numerator. Okay, so again, rational expressions. Oftentimes it may end up being or looking like a lot of work. Okay, but it's all things that we're familiar with. So if you just take your time, stay organized. Okay, eliminate things that you can eliminate to make it simpler. Okay, and you'll end up with the right answer. Okay, so quadratics. Okay, quadratics take 3 different forms. Okay, first we have standard form. Okay, the a value tells us the direction of the opening and the stretch it may have. So if a is positive, okay, our quadratic opens up. Okay, and the bigger the number a gets, the skinnier our quadratic gets. Okay, and then the c value is the y-intercept. So where the quadratic crosses the y-axis. Okay, next one is factored form. Okay, the a value again is the direction of the opening and the stretch. Okay, now m and n here, okay, give us the roots. Okay, you will hear a whole bunch of different words for roots. You might hear roots, zeros, x-intercepts, or even solutions. Okay, all those are where our quadratic crosses the x-axis. Okay, we'll talk about those more in a sec. Okay, and then the last form is, this is vertex form. Okay, a is the same thing again, the direction of the opening and the stretch. And then h and k, okay, give the vertex of the parabola. So it's just an ordered pair, so an xy. And it tells us the vertex. Okay, so it also gives us the max or the min. Okay, so we'll go through a bunch of examples here and what they will look like. Okay, so from this first one here, okay, my a value here is 1. Okay, which means I know it's opening up. Okay, and it does not have any stretch to it. When a is 1, it just looks the way we assume that a parabola will look. Okay, the only other thing I know here is that it crosses the y-axis at positive 4. Okay, so just to get a rough sketch, right now, I don't know if it crosses the x-axis. I just know that it looks something like that. Okay. So for the red one here, okay, my y-intercept is 5, okay, and because a is -2, okay, I know that it's going to be skinnier than this first example, and that it's opening down. Okay, so if I were to sketch that, it's noticeably skinnier, and it opens down. Okay, I'll clear those just so it's easier to see. Okay, now this next one. Okay, a is 3, and it's positive, so it's going to open up, and it's going to be quite skinny. Okay, and then I also know where my roots are. Okay, the only tricky thing about roots, okay, because they're the x-intercept, okay, we find the x-intercept when y is equal to 0. So if 0 equaled 3 times x plus 7, x minus 3, okay, the only way for this right side to equal 0 is if one of these is equal to 0. Okay, so if x plus 7 equaled 0, then x actually equals negative 7. Okay, just solving for x. And the same thing, if x minus 3 equals 0, x actually equals 3. Okay, so my roots here are actually have the opposite sign of what is shown. So x equals negative 7 is one root, and x equals 3 is the other root. So it looks something like that. Okay, so here a equals negative 4. So it's opening down and it's skinny. And then again, my roots end up being negative 1 and positive 4. Okay, so remember that you always, in factored form, we always have to flip that sign. Okay, so I have one at negative 1 and positive 4, and it's opening down. Okay, I'll clear this again. Okay, so this example, a again is equal to 1. Okay, and this gives me, this is vertex form, so this gives me the coordinates of the vertex. Okay, just like in factored form we had to switch the value of the roots, we have to switch the x value of the vertex. Okay, so my vertex here is actually at positive 3 and negative 5. Okay, so this one stays the same, but my x value has to change. Okay, so x is positive 3 and negative 5 is here. Okay, and from the a value this opens up. So it looks something like that. And this last example here, a is negative 1/2. Okay, and the coordinates of my vertex are negative 2, remember I have to flip it, and positive 7. So when a is less than 1, like it is in this case, I'm actually, my parabola is actually getting, it appears to be fatter, okay, than the normal parabola. Okay, so my vertex are negative 2 and positive 7, which is up here. Okay, it's opening down, and it's fatter than normal. Okay, so it looks something like that. Okay, so those are the 3 different forms that parabolas take. Okay, and they're all actually related to each other. Okay, the two that are the most easily relatable is when we're in standard form and we're looking for factored form, or vice versa. Okay, so we can flip between standard form and factored form by factoring a quadratic. Okay, and we can flip between factored form and standard form by foiling. Okay, so if we're not familiar with FOIL, okay, it just tells us the order in which we want to multiply our terms. So we want to multiply the first terms in the brackets, then the outer terms, then the inner terms, and then the last terms. Okay, so a few quick examples of those. So the first terms here are the x's. So we have x squared. The outer terms here are x and -2. Multiply those together. My inner terms are 3 and x. Multiply those together. And then the last terms are +3 and -2. Okay, and then again, we just simplify that. +x minus 6. Okay. If I have an a value in front, so here I have an a value of -2. Okay, it's usually easiest just to keep that till the end. Okay, and then distribute it in. So if I FOIL even if I simplify this, minus x minus 12. Okay, now it's usually easier to go ahead and distribute that in. So -2x squared plus 2x plus 24. Okay, and the third one here we had some this is a special example. Okay, so what happens is whenever we have a negative and a positive of the same value, okay, they end up canceling each other out. Okay, so my first one I would have a -2x, and then when I do my next step I have a +2x. Okay, so these, it's clear to see I have a -2 and a +2, they end up canceling each other out. And I'm just left with x squared minus 4. Okay, this is a special type of quadratic. Okay, we call it difference of squares. Okay, and if we can recognize it, it can save us some time. Okay, so factoring. Okay, anytime a question asks you to find the zeros, find the roots, or find x-intercepts, or find the solutions, okay, we're going to end up wanting to factor it. Okay. If you've not done factoring before, okay, probably the easiest way of doing it is to multiply the coefficient of the x squared and the last numbers. Okay, so for this next one, actually, sorry, I made a mistake. Let's change this to x squared plus 3x minus 4. Okay, go ahead and make that change and we'll continue with this one. Okay, so when I multiply the coefficient of x squared with the c term, I end up with just -4. Okay, so what I want to do is just go through the factors of 4 that I can add or subtract together to make the middle term. Okay, so in this case, I need to combine these two, the 1 and the 4, combine them to make a +3. Okay, so if I do a +4 here and a -1, okay, those will combine to multiply to be -4, and that add together to be a positive 3. Okay, so when I've done that, now for these ones it's rather simple. I just have x plus 4, x minus 1. Those become my two factors. Okay, so again, the zeros here would be at negative 4 and positive 1. Okay, because of what we talked about earlier. Okay, so for this next one, okay, by multiplying these two values together, I end up with negative 10. Okay, so again, I want to go through the factors. Can I combine 1 and 10 to be a positive 3? No. Can I combine 2 and 5? Yes, I can, but this is a positive and this is a negative. Okay, so now what I'll do is, I'll now break this 3x up into a negative 2x and a positive 5x. So my next step is negative 2x squared, okay, minus 2x plus 5x plus 5. Okay. So once I do that, I'm going to now divide this up into two separate items here and worry about them separately. Okay, so all I want to do is factor out the biggest thing I can factor out of negative 2x squared and negative 2x, which in this case is negative 2x. Okay, and I'm left with x plus 1. Okay, and I'll do the same thing on the other side. So I can pull a positive 5 out of both of these, and I'm left with an x plus 1. Okay, when you get to this step, you know you've done it right if these two terms are the same. Okay, so now when I get to here, okay, my two factors just become whatever you have in the bracket, okay, which in this case is x plus 1, and then the coefficients of those. So in this case, negative 2x plus 5. Okay. Now the good part about factoring is that you can always check just by foiling out what you end up with. So if I foiled this out, I would end up with negative 2x plus 3x plus 5. Okay, so when it's looking for my roots, okay, this first root is easy to find, it's just negative 1. Okay, the second root, okay, I set equal to 0, and then I solve for x. Okay, so when I do that, go ahead and try that, but you should end up with 5 over 2. Okay, so the last one here, so I have x squared minus 16. Okay, again, if you can recognize this, it'll save you some time. Okay, but all this ends up being is a difference of squares. So I have minus 4x plus 4. Okay, I took the square root of x squared and the square root of 16. Okay, and I just put a negative on one and a positive on the other. Okay, and this is a real crash course in factoring. Okay, but it's something that you might want to spend a lot of, not a lot, but spend enough time on it as to where you're comfortable doing it at a pretty fast pace. Okay, the faster you can get through factoring and foiling questions, just the more time you have for everything else. Okay, so some examples of quadratics. Okay, if we look at this picture here, okay, which of the following is an equivalent form of the equation of the graph shown, from which the coordinates of vertex A can be identified as constants in the equation? Okay, so there's a few key terms here. Okay, but what they're looking for is the form of the equation, okay, in vertex form. Okay, it's asking for the form of the equation in regards to the vertex A. Okay, so my vertex A here is 1, -16. Okay, so looking at the answers that it gives me, okay, this one doesn't have a 1 or 16, neither does this, neither does this. Okay, so just by process of elimination, okay, my answer here is D. Okay, and vertex form, again, I remember, is A x minus h plus k. So even just by subbing in those answers, I get x minus 1 plus 16, or sorry, that's minus 16. Sorry, there's a square here. Okay. So a fairly simple question that the way they ask it seems to be a little bit more difficult than it is. Okay. So the next example, if xy is a solution of the system of equations above, what is the value of y? Okay, so one thing I want you to notice, okay, is when we're looking for a solution to a quadratic, really what we're doing is, say this was x squared, say it was x squared minus 5x plus 6. Okay? So if this was my example, and I was looking for the solution of this equation, okay, really what I'm doing is I'm comparing it to y equals 0. So y equals 0 is a line, okay, and I'm comparing this equal to 0. Okay, so a question like this, okay, is I have this quadratic, whatever that might look like, okay, and I also have a line here. Okay, so if I were to rewrite this, it would be y equals negative 3x minus 3. Okay, so it would look something like this. Okay, so really what I'm trying to find now, instead of the zeros, okay, I'm trying to find where this line here intersects with my quadratic. Okay, which is the same thing I'm doing in this situation. Except my line, instead of being y equals 0, it's now negative 3x minus 3. Okay, so when solving a system, okay, that's really all I'm doing. Okay, so what I'm going to do is I'll rewrite my equation. Okay, and then I'm just going to set it equal to this line, x minus 3. Okay, so what I want to do now is just solve for x. Okay, there's actually a couple different ways to do that in this case, but probably the simplest way is to just expand and simplify. Okay, so I would be left, I'll let you do this one on your own. Okay, but I just foiled out this first equation. Okay, and ran through it fairly quickly. Okay, so moving everything over, I'm just collecting like terms right now. Okay, I'm just left with this. Okay, so I took this big equation, or I combined these two fairly big equations and just turned it into a nice quadratic that I can factor out nicely now. Okay, so by factoring this, okay, I would just end up with x plus 3, x minus 2 equal to 0. Okay, which gives me my two zeros at -3 and +2. Okay? So, it's now looking for the value of y, and I just solved for x. So now what I need to do is take these two numbers and plug in to either one of these equations again. Okay, so I'll plug in here. I just end up with 9 minus 3 equals 6. Okay, and again it says y is greater than 0. So I know that my answer is y equals 6. Okay, so again, a question that seems fairly complicated, but when I break it down, okay, it just becomes solving for a variable. Okay, and then when I get that variable, plugging in into one of the equations to get what I need to know. Okay. Okay, so this is a question that will come up. Okay. It doesn't give us A or B. Okay, but it does tell us that when we combine them, what our final equation will look like. Okay, so the first thing I'm going to do is I'm going to FOIL out this part here. Okay, when I do that, I have abx squared, okay, plus 7ax plus 2bx plus 14. Okay, so what I want to do here is similar to some of the questions we did at the beginning. I now want to compare, okay, my coefficients that I don't know to the coefficients that I do know. Okay, so here I know that a times b must equal 15. Okay, and then I also know that 7a plus 2b has to equal c. Okay, so if I know that a times b has to equal 15, okay, from the equation, I also know that a plus b has to equal 8. Okay, so for this to happen, the only way this can happen is if a is 3 and b is 5. Or it could be the other way around. Okay, that's why it's going to ask for two possible values. So if a is 3, okay, so let's say a is 3 and b is 5 for the first one. A is 3, b is 5. Okay, that ends up being 21 plus 10, which is 31. Okay, and now we'll flip that. We'll say, well, maybe a is 5 maybe b is 3. Now I end up with 35 plus 6, which is just 41. Okay, so two possible values for c are 31 and 41. So the graph of the polynomial p at x equals x to the 5 plus 5x to the 4 minus 10x cubed minus 20x squared plus 24x crosses the x-axis at the points negative 6, 0, negative 2, 0, 0, 0, 1, 0, and 2, 0. It says factor this polynomial completely. Okay, so sounds quite complicated. Okay, but knowing what I know now about zeros, okay, we know that zeros are where functions cross the x-axis. Okay? So, for a quadratic, say x squared plus 3x minus 4, okay, when I factor this, I end up with x plus 4, x minus 3. So my x-intercepts are at x minus 4, 3. Okay, and I also know that this happens when y is equal to 0. Okay, so I would have a 0 here and here. Okay. So now knowing this, okay, I know that x plus 6 is a factor. X plus 2 is a factor. Okay, here I could say x plus 0 is a factor, which I don't worry about, so just x. X minus 1 is a factor, and x minus 2 is a factor. Okay, so just making that a little bit nicer. Okay, so it sounds very complicated, but for any polynomial, not just a quadratic, okay, my x-intercepts, okay, will always give me what the individual factors are. Okay. Okay, so the end of our quadratic unit here is the quadratic formula. You're probably familiar with it. Okay, but when you're going to use this is when you can't factor equations nicely. Okay, but we can still get the zeros, okay, by plugging in those a, b, and c values into the quadratic formula. Okay, so this is the quadratic formula. Okay, the only thing we have to make sure that we do is to put however they give us the quadratic, that is that we convert it into standard form. Okay, so for this question here, what are the solutions of x squared minus 3 equals x? I have x squared minus 3 equals x. Okay, what I want to do is just put this into the right order. Okay, so now I know that, okay, a is 1, because there's an imaginary 1 here, so a is 1. Okay, b is negative 1. Okay, and c is negative 3. Okay, so then just plugging in, I have a minus 1. Okay, plus minus 1 squared. Okay, minus 4 times 1. times negative 3. Okay, all over 2 times 1. Okay, so the quadratic formula just becomes plugging in the values that I know. Okay, so x equals 1 plus or minus 1. I have minus 4 times 1 times negative 3, which is just positive 12, all over 2. Okay, which equals 1 plus or minus square root of 13, all over 2. Okay, and when I do that, I end up with D as the correct answer. Okay, so the only tricky part about the quadratic formula is that we make sure that it's in standard form before we get our A, B, and C values. Okay, and from there it's just plugging in and solving. Okay, so function notation. Okay, we're going to have to evaluate a function, okay, at whatever they ask us to evaluate it at. Okay, so we've been doing this for a while, but typically we have f at x equals, say, x plus 1, okay, and they might ask us for f at 2. Okay, whatever we do here, wherever we see an x in the equation, we then plug in a 2 for it, right? So it would just end up being 3. Okay? So they will ask us to do the same things, except they now might ask us, instead of plugging in a 2, we might have to plug in a whole another equation. Okay, so this example is, if g at x equals 2x plus 1, and f at x equals gx plus 4, what is f at 2? Okay, so the first thing we want to know what the function f is, so first let's say f at x equals g at x, which is 2x plus 1 plus 4. Okay, all I did here was take what they gave me. Okay, instead of having g at x there, I just plugged in what g at x actually equaled. Okay, so by simplifying this, we just end up with 2x plus 5. Okay, so f at x equals 2x plus 5, and they want to know what f at 2 is, so f at 2, this equals 2 times 2 plus 5, which equals 9. Okay, so fairly straightforward. Okay, this next example can be a little bit trickier. Okay, they give us what our function is, so f at x equals x squared plus x. Okay, so now what I want to do though is, now wherever I see an x, I'm going to plug in this whole bracket. Okay, so f at x plus 2 equals x plus 2 squared now, plus x plus 2. Okay, so I just replaced the x's that were by themselves with x plus 2. Okay, so now I can just go ahead and solve this like normal. So I'll FOIL the first one, and if I'll end up with x squared plus 4x plus 4. Then just rewrite the second part. Okay, and when I collect my like terms, I get x squared plus 5x plus 6. And I'm done. Okay? So function notation, they're very straightforward. Okay? Whatever they're asking for in the brackets, just make sure we sub that in for everything. Okay? Okay, and the last part will be our exponential equations. Okay? So these model situations in which a quantity is multiplied by a constant factor for each time period. Okay, they can be increasing with time. In this case, it would show what we call exponential growth, or it can be decreasing with time, in which it models exponential decay. Okay, so questions that deal with maybe interest payments or population growth or half-life from a chemistry class, these are all examples of when exponential functions are used. Okay, so y equals a times b to the x is the base function. Okay, but it can also be written as a, and instead of b, we can replace it with 1 plus r to the x. Okay, so a gives us the initial value. Okay, so what we're starting with. So, and b is the growth or decay rate. Okay, so if it's growing, obviously r will be positive. And if it's decaying or getting smaller, r will be negative. Okay, so our first example. So a researcher estimates that the population of a city is increasing at an annual rate of 0.6%. If the current population of the city is 80,000, which of the following expressions appropriately models the population of the city t years from now, according to the researcher's estimate? Okay, so the first thing we have to do is first determine, is this growth or decay? Okay, and obviously it tells us that we're increasing, so we know that this is going to be exponential growth. Okay, it tells us our initial value, so right away I know that a is equal to 80,000. Okay, and then the next thing I have to do is convert whatever percentage they give us into a decimal. Okay, so when I do that, I would be left with 0.006, the decimal. Okay, and just from following the previous slide, following the equation, I'm going to go 1 plus r. So 1 plus 0.006, and then in this case it's raised to the value of t, because we're going to go, we're going to measure this t years down the road. Okay, so instead of being x here, it's just a t. Okay, so by combining those, I'm just left simply with a is the correct value. Okay, one thing you may see here is they can easily just combine this part here and put 006 raised to the t. Okay, it's saying the same thing. Okay, but if you might see an example like this. Okay, so b, the reason b is incorrect is because the exponent t is inside the bracket, which just does not follow the formula. Okay, c is incorrect because we're adding these two numbers together instead of multiplying. Okay, and d is incorrect because we do not have a 1. So they're not going 1 plus 0.006. Okay? So this example. Okay, a car was bought in 2011 for $15,000. Okay? If it depreciates at 11% per year, what is the value of the truck in 2017? Okay, so the first thing we want to do is set up an equation for this. Okay, so our initial value is 15,000. Okay. Now we got to ask ourselves, is this growth or decay? Is it getting bigger or smaller? Okay, and in this case it's getting smaller because of the word depreciates. Okay, so it's losing value every year. Okay, so we'll go 1 minus r. Okay, and then again we'll use t here for years or time. Okay, so our r in this case is 0.11. I'm just again converting this into a decimal. So I have 15,000. Okay, 1 minus 0.11 t. Okay, which is 15,000. Okay, 0.89 t. Okay, so if I were to interpret this, okay, basically what this is saying is that every year, for every year that goes by, so for t, okay, the car is basically worth 89% of what it was the year before. Okay, so the number of years that have passed in this case is 15,000, 0.89. Okay, from 2017 to the 2011 is 6 years. Okay, and now I'm just going to plug these equations into a calculator. And when I do that, I end up with 74.54.72. Okay, so this question would obviously be in the section of the test that allows you to use a calculator. Okay, so again, after 6 years, this car that you bought for 15,000 is worth about half of what it would be when you first bought it. Okay, each year, again, I'll say this again, each year it's worth about 89% of what it was worth the year before. Okay, if they ask for the price of the car in, say, 2012, okay, the only difference here was instead of 6 for t, you would just plug in 1. Okay. Okay. So, bonus question here. Okay, this will combine a couple of different things that we talked about today. Okay, we'll take it up in our next class period. Okay, but I want you to try this question. Okay, it uses exponent rules and also some of the quadratic things that we talked about. Okay, so go ahead and try this question, and we'll take it up in the next class period. Okay, reminder that class is Monday this week. Okay, and here are the questions, the sample questions for this section. Okay.